All right, thank you very much. Very happy to be here. So today what we'd like to tell you guys a little bit is obviously how Ray helps Uber optimize marketplaces. We'll start out by telling you a little bit about what that means and what exactly we're doing. Then we'll tell you about how we adopted Ray and how that helps our system scale and our engineers to be more effective. We'll deep dive a little bit into just one of the applications that we migrated over to Ray. So the basic problem that we want to talk about is connecting business goals to marketplace decisions. So I hope a lot of you guys have used the Uber app. So you can probably imagine that a big part of like what our tech does is figure out how to set prices for riders and drivers in the marketplace. But on the other hand, having trips completed through the market is how Uber makes money. We also tell our investors and the public like certain goals we have. And so somehow there needs to be a connection between those two things. And that's what we'd like to tell you about. So fundamentally, I'm just going to, sorry. There's a optimization problem that we're trying to solve, which is, here's a business goal. And then we have some things under our control for different marketplaces. A marketplace might be something like, the city of San Francisco. And the city of San Francisco is pretty tightly coupled to, say, Oakland, but it's not coupled really to Los Angeles. And so we have certain things under our control that we can change, and these might be related to pricing or incentives or other pieces of the way the marketplace operates that affect outcomes in aggregate in the marketplace. So what we want to understand is how to control those. Okay, so what are we doing? We have basically built an automated allocation engine. And so there's different aspects of it, and I'm going to go into a little bit of detail about each of them. We train ML models on the vast amount of Uber data that we have on both users and the marketplace. We have control variables that we want to maximize. We have constraints that we want to make sure we hit, like don't lose money. We also want to be able to visualize efficiency metrics, and we want people to understand like what happens when they change the inputs to our plans. So I'm going to go, and of course, and so all of these steps we now use Ray for. So I want to talk a little bit about our modeling approach. So we actually use a two-stage modeling approach. The first stage is your sort of standard deep learning MLP based model, and that allows us to sort of integrate this sort of large volume of highly granular data that we have. And that uses sort of again, pieces of modeling that you're probably familiar with, embeddings, ResNets, regular fully connected layers. Then what we do is we use an adaptive search grid to generate a surrogate model. And the purpose of that is a fewfold. First is, if you can imagine that we're changing a few parameters in our model to understand the impact of, there's a lot of features that like in your model predictions don't change, like any historical feature. So we want to marginalize over those features in the surrogate model so we don't have to like sort of just keep inferring across them. Second, we can do some things like imposing shape constraints. Again, you can imagine for certain things, you might have some intuition about how the system should behave if you change it. One good example is something called like diminishing marginal returns, which is if you spend some money on something, you should get hopefully increased value, but the more you spend, the less you get. And so that's a kind of shape constraint we'd want to apply. And the last piece is we want to be able to control sort of like the extrapolation behavior of the system. So as we're training, obviously, we can only train on the sort of set of parameters that we've observed in reality. But we don't want to limit, our system to only apply those in the future. So we need to be able to allow the system to extrapolate from like sort of what's supported before. And we can, again, apply these kind of constraints in the surrogate model so that we know what happens if we go further away from what's happened before. In optimization, and we're going to go a little bit more detail here later, we use something called alternating direction method of multipliers. And the reason we mention it, first of all, is that it's an algorithm that's designed to be highly parallelizable. And so since we have a very large scale system that we're trying to optimize, it's a sort of key piece of technology for us. For those of you guys who know about optimization, it's designed to solve nonlinear and non-convex problems, which is pretty valuable for us. And I think those other parts I'll talk to in a later slide. So I'm going to hand over to Kaichen, who's going to tell us about how Ray helped us.
Thank you, Matt. And I'm going to talk about how do we adopt Ray into our tech stack. So for us, I think there are 3 goals that we want to achieve when we apply Ray into our tech stack. The first one, of course, is the application. We want to make our application faster, and I think that is the key that Ray want to bring us, that we want to make more parallelism to our functions, applications, program in order to get us speed up for our applications. The second one is code, because if you are a backend engineer or infrastructure engineer and you are trying to introduce a new technology or new library into your tech stack, you will find that there may need some end-to-end change to our code base. And usually it's very painful. Of course, I'm a very lazy guy, so I want to make my life easier. So I want to make this code migration cost very low so that we can move very fast and migrate to the new tech. And third thing is we care about the users. As you may already know, Uber is a company moving very fast, and we want to make our engineers, data scientists move very fast. So we don't want them to wait very long when we deploy new, for example, Ray clusters, or wait very long time to get the results. So we want to make the iteration speed much faster so that they can get the result faster. And we also build a lot of tools to help our users to improve their user experience. And this is a picture, screenshot from the Ray doc, and I believe many of you have seen this before. I will just briefly describe this one. So the Ray can be divided into 3 parts. The first part is cloud. So for this cloud part, it's just like providing you a Ray backend, and it can contain CPU, GPU, memory, disk, any kind of resource you may need to build your own Ray cluster. And the second one is Ray core. So Ray core, obviously, maybe you have written any Ray function before. So it's mainly for providing you with the base Ray functions like Ray task or Ray actors that can make your program run in parallel. And the top layer is Ray AI libraries. For this layer, it will provide you with very fancy machine learning API from Ray, like Ray Train, Ray Tune, Ray Serve, Ray Data. And for us, we have done something on each layer. So for the first layer, we work together with Uber Michelangelo team to build a Ray backend and infrastructure on Kubernetes. And under the hood is using KubeArray. And for this Uber Michelangelo team, is like a platform team that's supporting any Uber-related machine learning stuff that we want to build. So they will support us for this kind of stuff. And for the second layer, Ray core, that's the layer that we utilize the most. We heavily depending on this Ray core layer for distributed parallel computations, because as Matt mentioned, we have a lot of algorithms related to optimization and evaluation, and obviously Anyscale didn't provide us with this kind of APIs, so we need to play with them by ourselves. And finally, we achieved 5 times to 40 times speed improvement, and I will give you a much more deep dive later. And for the top layer, of course, we recognize that Ray Train and Ray Serve are very convenient API to use. So we also adopt the Ray Train and Ray Serve into our deep learning model training, and we find that it can truly improve our model training and serving for the speed. And before I talk about how do we adopt the Ray into our tech stack, I want to give you a quick snapshot about what does our application look like before we use Ray, so that you can understand the logistic that we apply Ray and why do we apply Ray like that. So we start with data frame. So at the left top or left bottom corner, you can see HDFS, and we load a large Spark data set from this HDFS. and we will start our application. And usually it will start with a data preprocessing part, which is using PySpark, and we run this on a Spark cluster. But after the data preprocessing part is done, it comes with some custom application algorithms, and usually it's non-Spark related. Because as Matt mentioned before, we have the optimization algorithms or evaluation algorithms. Also, it will be contained in this part. For our MLE or data scientists, they will come up with different kinds of algorithms using different kind of libraries. And for those libraries, they are always not related to PySpark. For example, they may use sklearn or SciPy or different kind of mathematic libraries with very strange names. So in that case, it becomes a bottleneck for Spark cluster, because as you already know that for Spark cluster, when you write any Spark function, for example, PySpark data frame operations, it can run very fast because Spark can recognize this kind of data frame operation and make them in parallel on different executors. But if you write something in pandas, especially for those customized pandas operations, by calling this strange libraries, there will be operation like you will collect the PySpark data frame to the Spark driver node only and run those kind of operation on the Spark driver node only. But for all the rest of the Spark executor node, they were just on their PTO, they will do nothing. So we want to avoid such kind of situation here, but previously we don't have a solution for this. And later, after this block, which is custom application algorithm, we will convert any processed data frame by different kind of libraries and convert it back to the PySpark, and we will continue to do data post-processing part, and it's still in the PySpark, and then we continue to write the output Spark data set back to HDFS. So that is the whole process our application looked like. So how do we change that? Just in summary, you can see that for our previous application, it is very Spark heavy, so that's the reason why we run that on a Spark cluster. But as you already know that not all the computation can apply Spark patterns, especially for the middle block, which is custom application algorithm. And as I said, for this middle one, it can just be done by a Spark driver only, but for the rest of executor, they are not useful. So we want to change such kind of situation. So that's the reason why we introduce this kind of architecture here. We use a hybrid execution mode here to support our use case. So previously we have the left column here, which is containing Spark driver plus Spark executors. Actually, nothing has changed here. But in addition to that, we add another Ray cluster that is like an external plugin cluster to this Spark cluster. So that in that case, any kind of Spark computation like data preprocessing or data post-processing, they will still running on Spark cluster only. But if we encounter some like pandas pattern or some strange pattern that cannot be run on Spark because Spark does not support that kind of things, but we find that actually Ray has a kind of feature that naturally support any kind of Python program parallel. So that's in that case, we think about why not just move all this kind of pandas-like computations on top of Ray instead of running that in series in Spark driver. So that is our initial motivation to do this. And our program logistic will become like this. So instead of just running our application on Spark only, first of all, we will have our data preprocessing work running on Spark. But after this preprocessing work is done, we will move this preprocessed data frame to Ray to do any kind of Ray computation, and usually it's done in pandas. And because, as Matt mentioned, we are doing the budget allocation for different cities, so we have a very clear granularity to do the parallelization here. Usually we divide into different cities, different weeks, and we do a parallel function for each city for each week. So that's the logistic we do the parallelism on Ray. And after Ray has done its job, we will just gather the result that is generated by Ray and send it back to the Spark cluster. So at the step 3, we will summarize the output from Ray, and then we may convert this data frame back to Spark data frame, or we do some analysis on this data frame and write the output back to HDFS. So previously, as I mentioned, we don't want our users to wait so long, and we want to make sure that our user, when they're doing their development, they can still have a very fast iteration speed. So we don't want to make our deployment and launching time for this kind of hybrid Spark plus Ray cluster to be very long. And there is another use case that for our engineers, for example, they always maybe change one line of code, or maybe just change one hyperparameter, and they want to run another testing experiment on our remote cluster to figure out whether maybe this one-line change or this hyperparameter change can have a positive or negative impact on our application result. So in that case, to accelerate that one, we introduce an intermediate layer, which is the cloud storage. You can regard this as just Amazon S3. It's just an object store for storing any files here. So, so for our previous design, I believe that is a kind of general design. We just merge any application code into our Docker image. But for generating that Docker image, it takes a very long time. So after our modification, if there is any application code change, we will first of all deploy this application code into this S3 cloud storage. And then we launch the Spark cluster and also Ray cluster. And then the Spark cluster and Ray cluster will load the application code from this cloud storage, so that for our application code, it does not need to be built inside the Docker image. It can be like real-time deployed and real-time be launched. And we can make sure that our Spark cluster and Ray cluster can have the same code version for our application code. And as a result, we have achieved less than 2 minutes deploy and launch time. So it can save a lot of time for our users to testing their jobs. And there is another issue we encountered when we designed this kind of infrastructure, because as I previously mentioned, we will have a Ray cluster that is working as an external server or plugin cluster to our Spark cluster. So we will have a data or task transfer between Spark cluster and Ray cluster. And sometimes it can be a bottleneck. So if our data size is very low, I think it will not be a bottleneck, because we can just transfer our functions or variables very fast from between Spark and Ray cluster. But if the data size is very large, then that can be a bottleneck. So in that case, we figure out a solution that is also to add an intermediate layer in between, and that is called HDFS. So, so for the previous design, if we want to send a data frame, large data frame from Spark to Ray, that means we need to, because Ray does not support any PySpark version data frame, so in that case, we need to, first of all, convert the data frame into pandas or some data frame format that Ray can support. And then we will do the serialization and transfer the data frame into Ray cluster, and Ray cluster will do this deserialization, which is very complicated. But after adding this HDFS intermediate layer, we can actually directly write the Spark data frame as a parquet into HDFS. And then we can utilize the Ray Data API to directly load the data from HDFS, which does not have any data gathering issues or OM issue in between. So that can make our data transfer much more stable than before. And we also develop a feature API that help user to select what kind of data transfer method they want to use. They can directly use ray.put or directly pass a data frame as a variable inside the ray remote function, or they can use our API just to upload the data frame to the HDFS and get that from the ray data. They just need to directly select that, and we already built the API for our users. And there are some other Ray backend support that we built together with our Uber Michelangelo team. The first one is Ray cluster stock killer. So because we find that sometimes Ray cluster is not killed properly. So for example, the Spark cluster is killed, but the Ray cluster does not have a command to kill it. So we will have a monitor to detect whether this Ray cluster is idle or just doing nothing, like zombie Ray cluster. We will just monitor that and kill this kind of zombie Ray clusters. And then we will have we also have a feature to improve our Ray log. Because if you are developing on Ray, you will sometimes find the log returned by Ray is not very comprehensive, or there is just no log returned from Ray. For example, sometimes Ray just kills itself by some worker node OM issue, or during the Ray cluster initialization, Ray has some issues, but it just killed itself but didn't reply anything. So we try to tackle this kind of situations and give back our user a very clear log. And the third one is Ray matrix visualization, and I think that is very straightforward. Ray has its own dashboard, which is called Ray Dashboard, and can help you understand CPU, GPU, and memory usage. And we also put those matrix onto the Grafana pages so that our users can debug these things better. And the other one is multi-ray Ray cluster control. So for this one, we develop a kind of parent to children Ray cluster control. So we initialize our parent Ray cluster, and this parent Ray cluster can provision or kill any children Ray clusters. So that is used for our original model training. So for example, when this parent Ray cluster want to train a model for region California or region NYC, this parent Ray cluster can just provision a children class. For the children class 1, it will train the region CA, and for the children class 2, it will train the region NYC. And after one region training is done, the parent Ray cluster will just directly kill the children Ray cluster so that it can save a lot of GPU and CPU resource for us. And for the fifth item, Ray train and Ray serve, of course, we use that for our deep learning model training and serving. And for the sixth item, we also built a notebook that is containing this kind of hybrid mode inside. So in this notebook, we provide an environment that is containing both Spark cluster and Ray cluster, and our data scientists, the MLE, they can do their experiment on top of this notebook. And the good thing about this notebook is the environment provided inside this notebook is just as same as our production environment. So after they make sure that their code is working inside this notebook, so the same code will just be working inside our production. So it's very convenient. We don't need to do any migrations. And this is our benchmark result. As you can see, we have applied the Ray to different kind of applications. We applied to our surrogate model training, and also national city level evaluation jobs, and also we applied to the ADM optimization. So we actually not only apply Ray into ML only, we also apply our Ray into optimization area, evaluation area, and I think that is the main takeaway I want to show today is Ray cannot just be used for machine learning. And I think that is the main topic for this Ray Summit. I attended a lot of presentations, but I always heard the topic related to the LLM or machine learning, the big models. But I think the main the main task Ray is being created is for parallelization and distribution. And machine learning is a kind of product, a result built on top of distribution and parallelization. And in addition to that, I believe you already paid attention to this big number, which is at the right bottom corner. So we have done a 47.8 times improvement for our optimization algorithm. So I will let Matt to introduce you how do we achieve this kind of improvement.
All right, thanks, Kaichen. So we will show a little bit of math, but so this is sort of on the right is a diagram of what the ADMM loop looks like, and I'm just going to explain briefly connected to the math. So you don't really have to understand this, but what I want you to take away is there's two parts of the optimization problem, and one of the parts is this thing F sub C, which is something which we've split up over, in our case, cities. And then there's G of Z, which doesn't have the C subscript. So that's something that applies for the whole problem. Okay, so that tells you that part of the problem is parallelizable and part of the problem is not. And so what we wanted to make use of with Ray, obviously, is to parallelize the parallelizable bit of the problem. And so then the second bit of math is the second set of equations. So for those of you who are familiar with optimization, there's just always some rules that you do to update your variables. And you can see that two of these, B and Z, have something that says argmin, which means we actually have to do another optimization. And so that's the part which is definitely computationally complex. And if you do this sort of in series or try to do this in a single solution, it's very slow. So what we did is basically broke up that part, the first one actually, BC, this argmin, into per city, per week problem solutions. And that is the part that runs on Ray. And so that allows us to run things in very parallel fashion. Then you get those results back. In our case, luckily, Z of K, this argument, is actually something you can solve with just a formula. It has an analytical solution, and obviously the Y sub K thing is trivial. And so I'm going to go to the next one. So Ray is how we basically solve, in our problems we have thousands of individual problems that we need to solve in every iteration loop. So that's where we use leverage Ray, and those can run in parallel. And then, the Spark driver, as Kaichen explained, is sort of where the sort of central algorithm runs. And so we are able to summarize the results from Ray and decide the next step. And if it's optimal, we can stop, and if it's not, we have to keep looping. And so a loop, a normal problem might take 1,000 loops with 1,000 city weeks. If we had to run those in some other way, would make this sort of problem not sort of practically feasible. Thank you all for your attention. That's all we have today. Uber is hiring both for Ray Infra and the kinds of problems we talked about. And I think we have a minute or two for questions. Yeah.
My question is about your using HDFS for transfer the data. When you were saying HDFS, do you mean you're uploading to some storage within Uber and then just pass and then just read it back to Spark or whatever reverse way? If so, then how do you manage this data? Because eventually maybe you just use it once and then you just keep this on the hard drive forever. How do you manage it?
Yeah, so the question is basically, is the HDFS piece just loading it, saving it somewhere in Uber on an HDFS cluster, and then if so, how we manage that? Kaichen, do you want to take it?
Yes. So for those data frame or Parquet files that it just need to be useful once, we would just store that into a temporary directory, and it will be cleaned periodically.
So you have a TTL.
Yes, we have a TTL. I think for those data frames just used for maybe once, it will just have a 3 days TTL. But if you need to use it multiple times, it will have a longer TTL.
You guys like explored removing Spark from the pipeline with something that's friendly with Ray, like polars or something?
So is your question related to like, can we just directly use Ray and deprecate Spark? Oh, so for us, because we mentioned that we are heavily depending on Spark data frame operations. Ray has a shortcoming that it does not naturally support any PySpark data frame operations. So if we want to like fully deprecate Spark and just use Ray, that means we need to like convert all this data pre-processing Spark algorithms or post-processing Spark algorithm into maybe pandas-like or some patterns that can be supported by Ray. But this kind of migration work will be huge because we have a lot of algorithms that is previously writing in PySpark.
Should we take one more?
Yeah, so you mentioned that like the application code is uploaded to S3 and then read by the Spark cluster or Ray cluster. So what if like this application has different type of like library dependencies? How do you manage those on the Ray cluster or Spark cluster?
Oh, so for now, we just make sure that our Spark cluster and Ray cluster having the same dependencies. So we make sure that all the dependencies that are required by Ray or Spark are just pre-installed in one Docker image.
All right, thanks everyone. We're happy to take questions or talk on the side.